Let's talk about database performance. Database performance in MongoDB is driven by pretty much the same thing that every database is driven by, which is, are you going to use an index to resolve your query or not? So indexes turn out to be the single most important factor in database performance in MongoDB and in relational databases. So this will be a review for a lot of you, but I want to take you through the basics of indexing and what it is and why it's so effective. So if you look at MongoDB or any other database, it will store its data in these large files on disk, and this is supposed to represent some sort of collection. There's no particular order for the documents on the disk. It could be anywhere. And if you ask for a particular document and you do a query, what the database is going to have to do by default is scan through the entire collection to find the data. Now, this is called a table scan in a relational database, and it's a collection scan in MongoDB, and it is death to your performance. You do not want to have to scan your entire collection for your data if the data set is large, because it'll be extremely slow. So instead, we use indexing. So how does indexing work? Well, it's pretty straightforward. If something is ordered, like for instance this list is ordered alphabetically, apple, banana, kiwi, pear, then, and even if it was very long, it's very quick to find something within the list, right? Because you can use a binary search to do it. So finding something in an ordered list, in a sorted list, is quick. Finding something in an unordered list is slow. What we do is we keep our keys ordered. Now, we don't actually keep them linearly ordered like this in MongoDB. We use something called a B tree. But conceptually, you can imagine it looking like this. And if I'm looking for, let's say, banana, I can quickly search, find the item, and then have a pointer to the actual document inside the collection. This is the key. So indexes in MongoDB are an ordered list of keys. So for instance, you could have an index on name, and then an index on hair color, and there could be another index on date of birth or something. Now the order is important because conceptually the way the index is built is that name will be at the top level. So here are my names, and this might be Amy and John and Zoe. Well, maybe Zoe's over here. Now within this, the hair color is sort of conceptually over here. So for all the Amy items, we've got brown hair, blonde hair, I'm going to put BL for blonde hair, black hair, and they're repeated for every item. So there'll be some brown hair here, black hair here. And then finally within this, pick a new color, you might have a bunch of items for date of birth. So here's my hair color over here, my name is at the top level, and then finally I've got this date of birth item at the bottom. So if you provide me the person's just their name, then I can go into the index and I can find all the Johns. And if you prefer to provide me the hair color, I can break it down and find all the brown-haired people. And at the very bottom of this, of course, is going to be pointers into the actual data. Now these things are going to represent keys in the Mongo document that we've decided to index. In order for a database to utilize an index, you have to give it a leftmost set of items. So you can give it just the name, or you can give it just the hair color, name and the hair color, or you can give it the name, the hair color, and date of birth. If you provide me just the date of birth, I can't do much conceptually with the index, because the date of birth is down here at this level. So I would need to do a binary search through here, then do a binary search through this one, then do a binary search through this one, etc., etc., etc. Instead, I need to start at the top. And this is true whether or not I'm doing a query, or I'm doing an update, or I'm doing a sort, because sorts also will use an index to sort their values. So for instance, if I pull a bunch of data out of the collection and want to sort it by name, well, the database can use this index, which we just defined, name, hair color, date of birth, to do the sort. Now one other point I want to make is that every single time the database wants to insert something into it, or you want to insert something into the database rather, this index needs to be updated. And that updating takes time. So although reads are faster inside a database, writes are a little bit slower if you have an index, because the index needs to be updated. And so indexes are not costless. They take space on disk, and they also take time to keep updated. And that's something to keep in mind. So you don't want to have an index on every single possible way you're going to query the collection. You instead want to have an index on the ways you're most likely to query the collection. Let's go through one or two examples, talk about the index. Say I have an index on A, B, C, and I do a query on B. Can the index be used? The answer is no. If I do a query on A, yes. If I do a query on C, no. If I do a query on A, comma B, yes, it uses two parts of the index. A, comma C, it uses just the A part. So, and it ignores the C part for the purposes of doing the search on the index. So I hope that kind of gives you a feeling. All right, so now it's time for our first quiz. Which optimization will typically have the greatest impact on the performance of a database? Adding more memory so that the working set fits in memory? Adding a faster drive so that the operations that hit disk will happen more quickly? Replacing your CPU with a faster one, say 2x as fast? Or adding an appropriate index on a large collection so that only a small percentage of the queries need to scan the collection?